All right, we are about to start another optimization technique. Okay, and so this is going to be the build-up to golden section search, and that's why I'm calling it not golden section search. Is this technique that we're about to do will add a little something extra to it tomorrow, which will make it golden section search. It'll make it more efficient. Okay. But is what you can see here is we have some minimums that we're trying to find, and we've bracketed that minimum between an x lower and an x upper. So this should feel kind of like bisect at the moment, except for we're actually going to divide our interval into more pieces. We're not going to just cut it in half. Okay, we're actually going to have, confusingly at first, an x2 and an x1. Okay. And so you might be wondering, why is it that I've written x2 here to the left? Because right when we look at number lines, we like to count left to right. But is what's going on is actually to get this calculation for x2 is what we've done, and x1 I should say as well, is we've done, say, x1 is equal to xl plus some constant times the length of the interval. Okay. And so let's see what that probably looks like. It's, what do y'all think? Maybe a quarter of an interval, or this looks like a quarter of the way. So is what we really did. To get to each one of these is, say, for x1, we went 3/4 of the interval length to get to x1. And to get to x2, we've done x upper minus this constant times xu minus xl. Okay. And again, based on how I've sketched it, it looks like k is probably 0.75 approximately. Okay. And we can choose this constant to be different things. But the confusing part that I want to clear up here is that we're calling this one x1 because we get there from going from x lower, and we're calling this one x2 because we get there from going from x upper. Okay. So that's all that's going on there. Okay. But now the next thing is, well, how do we decide whether to, or how do we decide what to do next? Okay, because we haven't actually done anything other than divide our interval up. And while we're at it, let's divide this other interval up in the same fashion. Let's maybe call this one x2, and this one over here x1. That looks about right. Okay. Well, what we're going to do in both cases is we're going to compare the function value at x1 and x2. Okay. So let's do that. We're going to say f of x1, and we're curious how it compares to f of x2. Okay. All right, well, if we look here, it looks like x1 has a smaller y value than f of x2. Okay. So we have f of x1 is less than f of x2 here. And let's go ahead and do the same thing over here, and it looks like we have the opposite thing occurring. It looks like here f of x1 is actually the bigger one. All right, and so yeah, the question is, well, what does this tell us? What does this tell us if, say f of x1 is less than f of x2? Okay. Well, that tells us, in fact, that the minimum does not occur in this interval. Okay. Assuming that we bracketed it well. So we're going to get rid of that section. Okay? And so if we get rid of that section, let's think about the most natural way to assign things. Okay? So the most natural way to assign things from here would be to maybe say, well, then x2, and actually I'm going to rewrite that a little bit different. X lower is going to be equal to whatever x2 was. Okay? X upper can stay as x upper. And we'll make those same calculations that we talked about a minute ago. We'll say, hey, to get our new to get our new x1 and x2, well, one of these is going to start at x lower. Okay. And it should be, and I should actually write the correct thing here. x1 is equal to x lower plus, again, some constant times x upper minus x lower. And we'll get our x2 in the same fashion, except for it'll be x upper minus k times xu minus xl. Okay? And then if we're over here in this situation, the question is, how are we going to reassign things? Well, because f of x1 is greater than f of x2, we know that our maximum, or sorry, our minimum does not occur in this region. So we can cut this out, and this will become our new x upper. Okay, so x upper is equal to x1, and x lower can stay itself. So we wouldn't actually need to reassign it to itself here. Okay. But then to calculate x1 and x2, it's going to be in the same fashion. In fact, I'll just copy this. There we go. And we're just going to keep repeating this process, and it's going to keep closing in. It's going to keep closing in on that minimum. Okay. And so what we're going to do is we're just going to create a very, let's put it this way, it's not going to be a complicated version of this algorithm. We're going to just run this thing, say, 10 times on an example. Okay. And is what we'll do tomorrow, again, is we will add in a little bit more detail to make this efficient. And we'll have a really interesting way of evaluating the error, kind of like with bisect method. Okay. All right, well, let's go ahead and switch over to MATLAB. All right, now we're in MATLAB, and let's talk about what we have here. So we have xopt, which is going to be the x value that results in optimizing our function. Okay, so let's maybe write that. And here when we talk about optimization, we're going to be talking about minimizing. So I'm going to actually even write in parentheses. Okay, that looks good. And then, of course, f will be the function that we're trying to optimize. So I'm going to just say function f. And then our xl and xu, those are just going to be our brackets for this root. Okay. So xl should just be a little left to the root, x upper should be a little bit to the right of the root. Okay. All right, so next, let's go ahead and maybe start in some of these first calculations. Like, let's say we want to compute, and maybe I'll pull it up here. Maybe we want to compute this piece that we're adding every time. Let me highlight it. Yeah, right here. This piece that we keep adding to x lower and x upper. Why don't we maybe compute that first? Okay. So we have d equals, okay. And why don't we choose the constant here ourselves? Let's say it's 0.75 like we were doing, okay, or approximately 0.75. And this is, again, x upper minus x lower. Okay. So this is the number that we will add and subtract from x lower and x upper. All right, let's go ahead and compute x1. So we have x1 there. And this should be equal to xl plus d. And x2 should be equal to x upper minus d. Okay. So that'd be our first x1 and x2. And for the sake of simplicity, okay, we're not going to build in a while loop that has anything to do with error. We'll save that for tomorrow. Let's just start off again with, just a basic for loop. We're going to perform this 10 times. So I'm going to I equals 1 to 10. And there's two situations here. Okay. So if F1, which we'll explain what that is here in a second, if F1 is less than F2, what will we do? Okay, and we'll see. And the other situation would be if F2 is greater than F1. But I want us to see that this is the first case we have here. Let's go over. Okay. Right? F of x1 was less than f of x2. Okay. So I'm going to need to also define those. So F1 is equal to, and F2 is equal to, and we're going to just say f of x1. Suppress that, and F2 can be f of x2, and we'll go ahead and suppress that as well here. Okay. So if F1 is less than F2, the question is, well, what are we going to do? Okay, well, let's go back. We said that we would make x lower be equal to x2. So I'm going to say x lower is equal to x2. In this case, remember, x upper was going to remain the same. So if we go back and look, xu equals xu. So I don't actually need to write that. But something I didn't write is that for now, x1 is our best estimate at the minimum, right? It was smaller than x2. So we'll write in here as well that x opt, I'm going to write it first, x opt is equal to x1, okay, but we can suppress all that. Okay. So there's x lower is taken care of, x upper is taken care of. So now the question is well, what's x1 and x2 going to be? Well, we'll come over here and we can just copy and paste our x1 and x2 because we're going to find this in the same fashion. Not what I wanted to do. There we go. All right, and we'll think about whether we're missing anything or not here in a second. Let's think about this other scenario. So if it had happened that F2 was the smaller one, okay, we'd be switching a lot of these up. We'd be saying, hey, the optimum here is actually at x2, and we would actually assign, let's go over and look. Over here we assigned x upper to be x1. Okay, so we have x upper is going to equal x1. And then we'll compute our new x1 and x2 in the same fashion. We'll just add the multiple of that number each time. But we're going to need to include some of this detail here. So what we could do is we could put in here, oh, let's see. We're going to need to recompute this d, right? If we've changed this, if we've reassigned some of our stuff, the interval length is going to change, which means d is going to change, right? Because x upper minus x lower is going to be a different number, okay? So there's that, and I'm going to input that in both of these. And let's see, are we missing anything else? It might also be helpful to also go in here and compute F1 and F2 again, because as we run through our next iteration of the for loop, it's going to need an F1 and F2 to compare, a new set of them. So we'll go ahead and we'll do that. And then we're going to need an end for the if statement, and we're going to need an end for the for loop. Okay. And let's go ahead and save it and test it out. Okay, so I'm going to hit save. Okay. And notice again, not Goldman and not Goldman, the name of the file and the function match. And let's go over to our oscillating current. Okay, so we had found the maximum, right? The maximum using our first derivative and bisect, okay? And if you want to see what those look like here again, we can take a peek. I just need to change this to a function, and I'm going to get rid of some of this other stuff. We don't need our plot here anymore, or any of this. We just need our function, its derivative, and then we should be able to find the x max here. Okay, and this is 0.2249. Okay, and if you want to see the more decimal places, we can do that as well. Format is equal, or yeah, format long. Okay, and why don't we? So we have this as x max. We'll save it as that. Okay, so there it is. And I'm going to go up here and I'm going to do the same thing we did recently. Clear vars except x max. I'm gonna hold on to that x max. Okay, so next thing is we actually don't need this derivative anymore. Okay. Let's go ahead and delete it. Okay, and we'll delete this bisect portion here as well. Okay. And so we'll go in here and we'll do not Goldman. Okay, and then with our Goldman function here, the first input should actually be the function. So let's see here, our function is named I. And then to try and bracket this, we could say 0.1 to, how about 0.4? Right, we saw it was 0.22 something. So we actually already have a pretty good idea on what it is. But let's go ahead and test this thing out. Okay, we're going to go ahead and hit run. And maybe let's see what our output was supposed to be. It's supposed to be x opt. I'll just write that in here. X opt. Okay. And so you can see here that our x opt is actually pretty far off, okay, from the 0.2. So there could be a few different things happening here. One of them is that maybe we just haven't done enough iterations yet. Okay. Maybe if we upped it, that might fix it. Let's maybe see if that'll make the change that we need here. So we just had 10 iterations. Let's maybe just try 20. Bump it up an extra 10. Okay. It could also be that this is diverging. Okay. Let's go ahead and go back. Okay, so it seems to be closing in on 0.4. So I'm starting to wonder now, is it that this 0.4 is too far off? Okay, and maybe we'll go back and look at the graph here in a little bit, but if there's another, actually I see two issues here right now. One is our Goldman is meant for finding minimums, and we're looking for a maximum. All we got to do to fix that is put in a negative here, right? If you put a negative there, all your maximums will become minimums, and all your minimums will become maximums. Okay? So now we've made it to where that maximum we're looking for will now be a minimum on the graph. But again, all we really care about is this x value right here. So let's go ahead and hit run and see if that fixes it. That was the trick. It wasn't that we had bracketed this too widely, okay? Because that is a possibility. Okay? When we are performing this, we do expect that this region that we're cutting off, in either one of these cases, that region that we're cutting off does not contain the minimum. So if this is really curvy and we've bracketed it to where there's multiple minimums in between the bracket, we could definitely run into some issues. And that's what my fear was, but it looks like we did fine. Okay. So that's it.